So we've been looking at graphing our cosine functions, our sine functions, cosecant functions, and secant functions. Now let's get into graphing tangent and cotangent functions. And so looking at y equals tangent of x here, let's rewrite this in terms of sine and cosine. So recall that tangent of x can be rewritten as sine of x over cosine of x. We're worried about values which set our denominator equal to 0. And those are values we have to exclude from the domain because that's not giving us, that input is not giving us back a real number. And those are the values that set our denominator equal to 0. Those are our vertical asymptotes. And so looking at when cosine of x is equal to 0, that's at when x is equal to pi halves, 3 pi halves, 5 pi halves, etc. And it's plus or minus these values. And so a way we can express that, notice those are odd numbers in between there, the pi halves. And so these are values that are going to give us our vertical asymptotes. I'm going to just call it VA, short for vertical asymptotes, or x is equal to, and a way that we can express an odd number are 2k plus 1 or 2k minus 1. All times pi halves. We're going to consider k as an integer. And so recall integers are coming in from negative infinity in the form of -3, -2, -1, 0, 1, 2, etc. So we're going to have vertical asymptotes here. Those, again, are the values we have to exclude from our domain. So our domain are all real numbers except those. So writing that in set notation x such that x cannot be 2k plus 1 times pi halves. And k is an integer. And our normal period for tangent of x, recall, is pi. Let's graph where those vertical asymptotes are really quickly. And so we have pi halves. We have 3 pi halves. Actually, I'm going to give myself more room. We have negative pi halves. Negative 3 pi halves. So these are our vertical asymptotes. So finding these vertical asymptotes when you're graphing tangent of x and cotangent of x are really helpful. And based off of where our vertical asymptotes are, the midway point between those two values, those are going to be where we're crossing that x-axis, or if we're doing shifts, the midway line. And so notice here, if our midway line between negative pi halves and pi halves, one period length is pi, is at the origin 0, 0. If you plug in 0 into our function of tangent of x, or if it helps you, sine of x over cosine of x, sine of 0 was 0 and cosine of 0 was 1. So 0 over 1 gives us 0, 0. So remember at pi force, cosine and sine were the same values. Cosine of pi force equals sine of pi force, which was √2 over 2. And so if we look at that, tangent of x at pi force is equal to 1. And then, so we have a point here at pi force 1. And then the halfway point between negative pi halves and 0 is negative pi force. Well, negative pi force, our sign value was negative √2/2, but cosine of negative pi force is positive √2/2. And so that would give us back a y value of -1 at tangent of negative pi force. And so this graph in between these vertical asymptotes, it kind of looks like our cubic function. Kind of more curvature in there. So we can graph, it's just going to repeat itself every pi. And so that's what our tangent of x function looks like. And notice here our range, we're hitting all of our y values. So our range for our tangent function is -infinity to infinity. So similarly, we can graph our cotangent function. So looking at cotangent of x, so y equals cotangent of x. Let's rewrite that in terms of sine and cosine. So recall cotangent of x. This is the same thing as cosine of x over sine of x. So values which set our denominator equal to 0 are our vertical asymptotes. So we're going to have vertical asymptotes when x is equal to, well, 0, pi, 2 pi, 3 pi, ... or negative pi, -2 pi, so plus or minus. And we can express that by pi times k, or k pi, k times pi, where k is an integer. Our domain are all real values, or all real numbers, except for x can't be any of those vertical asymptotes. So x cannot be plus or minus. I actually don't need that plus or minus when I'm talking about k being an integer, because that actually includes that, unless I'm just talking about positive integers. So x cannot be k times pi. So let's graph those vertical asymptotes, and that will help us see the shape and graph of cotangent of x. So a vertical asymptotes, 0 was one of them. So x equals 0, that's the y-axis. We had pi, 2 pi, negative pi, -2 pi. So just like tangent of x, that midway line, halfway on that midway line is where it's going to be crossing. And so looking at this, I know between 0 and pi is pi halves. So halfway between here is pi halves. So cosine of pi halves is 0, sine of pi halves is 1. 0 over 1 is 0. So here at 3 pi halves, I'm also getting 0. So the halfway points between our vertical asymptotes are where we're crossing that midway line, which is the x-axis, unless we had a vertical shift on our graph. And so now let's look at what's happening at pi force. Well, cosine and sine of pi force are the same thing, √2/2. And so if we're looking at root 2 over 2 divided by root 2 over 2, we're getting back 1. We have a point here, cotangent of pi force is 1. But at not negative, at 3 pi force, that's in the second quadrant. Our second quadrant cosine is negative, and sine is positive. And so we're going to get a point at -1 here, cotangent of 3 pi force. And so that graph here of cotangent of x is similar. I'm not the best shape. It's similar to the tangent, except that it's shifted over 90 degrees, which makes sense because remember, we had those were cofunctions. Tangent of x was the same thing as cotangent of pi minus x. Except that this is also a decreasing function where tangent was an increasing function. And then our range is that we're hitting all real numbers. So -infinity to infinity. So those are important features of that cotangent of x graph. And again, cotangent and tangent, I mentioned this in another video, do not have amplitude. Only ones that have amplitude is sine function and cosine function. And one other thing in here is that, I don't remember what I was going to say. Oh, the period, knowing the period of these. Sine, cosine, cosecant, and secant functions all have a period of 2 pi, but tangent and cotangent functions have a period of pi. Unless we start playing with our argument and multiplying that by another number, that variable other than 1. So let's look at a couple more examples, but for this next example, you have to remember how to take a composition of two functions. So in front of us, we have, recall, we have a parentheses f with a little circle in between g and parentheses x. So that reads f of g of x. And this, recall, meant that you're taking your equation of g of x, and wherever you see an x in f of x, you're replacing that x with that g of x function. To me, it looks better when you write it this way. It makes more sense. So let's look at an example really quickly where we're given what f of x is and what g of x is. And so here we're given that f of x is equal to tangent of x and g of x is equal to 4x. We want to find f of g of x and g of f of x, and then we want to graph each of these functions. And so let's look first at f of g of x. So our g of x function is 4x. And so we're going to take that 4x and we're going to plug it in wherever we see an x in f of x. And so f of g of x this can be rewritten as f of g of x, which is 4x. And then again, this is just saying we're taking our 4x and we're plugging that in wherever we see an x in our f of x function. So f of x is tangent. I see an x there. I'll replace that x with a parentheses, and we're going to replace that with 4x. So that's what f of g of x looks like. So normally, composition of functions, order matters. You're not going to get the exact same thing if you change your order, usually. So looking at g of f of x, this is saying we're taking our equation, this time tangent of x, and we're going to plug this in whatever we see in x in g of x. So we could write this as g of f of x, which is tangent of x. So taking tangent of x again and plugging it in wherever we see an x and g of x. So I have 4 times I see an x there. So I'm going to replace that with tangent of x. And so notice we got 2 different things. F of g of x was tangent of 4x. And g of f of x was 4 tangent of x. So that's gonna look different when we graph these. So let's first look at tangent of 4x. Tangent, we normally, one cycle, if you remember, was between negative pi halves and pi halves. So let's use that fact to look at what's happening. This argument is not just x, it's 4x. So that is going to affect our period. And so let's take that 4x and let's sandwich it in between a normal cycle, one of them for tangent, which is between negative pi halves and pi halves. In this inequality, I'm not putting the equal sign there because those are values where I have a vertical asymptote. And so those are values where x is undefined. So I could get rid of the 4 in front of the x by dividing everything through by 4. Or another way to think of that, since we're dealing with fractions on each side of the inequality, let's multiply everything through by 1/4. And so if I multiply 1/4 by negative pi fourths, this gives me negative pi eighths. This is less than 1/4 times my 4x here, that gives me x, is less than, and 1/4 times my pi halves is pi 8. And I said pi 8's over here, but I wrote negative pi halves, so negative pi 8. So I know that those are where my new vertical asymptotes are. So let's put that on here. So if it wants me to graph more than one period, we would want to figure out what this length is. That length between negative pi eighths and pi eighths. Well, a length we can find by the bigger value, pi eighths in our case, minus the larger value, negative pi eighths. And so this would give me pi eighths plus pi eighths plus pi eighths, which is 2 pi eighths. Which is reduced down to pi fourths. So subtracting pi fourths, or 2 pi eighths, from negative pi eighths, that's going to be negative 3 pi eighths. I think I made an error. I just found, let's keep it as 2 pi eighths. I just found that length here as 2 pi eighths. So to get the other vertical asymptote, I'm adding pi eighths, 2 pi eighths to pi eighths, which this should be 3 pi eighths. And if I subtract 2 pi eighths from negative pi eighths, that would give me my vertical asymptote over here, which is negative 3 pi eighths. Okay, so if it wanted our period, we know our period is 2 pi eighths, which we can reduce. It was easier to keep it with that common denominator when we were adding and subtracting it. But our period is pi fourths. And so for tangent, we're going to look at the halfway point between our vertical asymptotes. That's where it's going to be crossing the x-axis at the halfway mark between pi eighths and 0. This was pi 16ths. That would give us 1. And at negative pi 16ths, we're going to have negative 1. So we're getting our graph of tangent of 4x. So our domain, we're going to have to exclude negative pi eighths, 3 pi eighths, 5 pi eighths, plus or minus those values. So now let's look at what's happening when we have that 4 in front of the tangent of x. Well, that doesn't affect our asymptotes of tangent of x. What it's affecting is it's stretching it. And so negative pi halves so negative pi halves and pi halves, those were our asymptotes with a period of pi. Three pi halves was another asymptote, negative 3 pi halves. Denoting our asymptotes by dotted lines. Midway point is where it's crossing the x-axis between those asymptotes. So at the origin, at pi, negative pi. Those values, though, where tangent of x was equal to 1, we're now multiplying by 4. And so here at pi fourths, normally we would have 1, but this time we have y equals 4. So we're vertically stretching it. And at negative pi fourths, we had negative 1, but now we're going to have negative 4. And so we got these important points so that we can see the shape of our graph. So it just looks the same, except it's stretching more. There's some curvature in here. So the constant outside of the tangent of x did not affect the period, where the constant times the value of x in the argument did affect the period. So now let's look at another thing, another example. So you'll have an example where you have to find the average rate of change of a function, a trigonometric function, on some interval. And so we're called to find the average rate of change of f of x on the interval x equals a to x equals b. You're basically looking at the slope between those 2 points. And so we're looking at our y value when x equals a and our y value when x equals b. And so we're looking at f of b minus our y value at a, so minus f of a, all over the change in our x value. So b minus a. So that's the average rate of change of f of x on the interval a to b. And so now let's look at this and apply this with trigonometric functions. And so in this example, find the average rate of change of f of x equals secant 2x from 0 to pi 6. And so we want to look at f of pi 6. So we're going into our function f of x, so secant. And wherever we see an x, so 2 times I see an x there, we're replacing it with pi 6. So we're looking at f of pi 6 is secant of 2 pi times pi 6. We can reduce this. This is secant of pi thirds. If it helps you, rewrite this in terms of sine or cosine. So this is 1 over cosine of pi thirds. Cosine of pi thirds, same thing as 60 degrees, is 1/2. So secant of 2 pi 6 is the same thing as 2. So we have f of pi 6 is 2. Now let's look at f of 0. So going in and plugging in 0 wherever we see an x. So we have 2 all times 0. Secant of 2 times 0 is secant of 0. Cosine I know of 0 is 1. So we have 1 over 1, which gives us 1. And so now looking at the average rate of change, the change in our y value, so we have a y value here of 2 minus the y value here of 1, all over the change in our x value. So we started with pi 6, f of pi 6 on top, so we want our x value pi 6 down here in the denominator, minus 0. So let's reduce this, and we don't like fractions within fractions, so let's rewrite that so it's not a complex fraction. So we have 2 minus 1, which is 1, all divided by pi 6 minus 0, which is pi 6. So this is the same thing as 1 divided by pi 6, or 1 times the reciprocal pi 6, which is 6 over pi. So the average rate of change is 6 over pi. Okay, so that is the end of looking at graphing the other trigonometric functions. And in this video, it was just tangent and cotangent, and then some other extra information using algebra for secant, and we didn't have to do cosecant. So let's get into the next section. So I'll restart a new video for that section, which will talk about phase shifts and sinusoidal curves.